Pick IR spectroscopy. IR spectroscopy is used for determining functional group for organic molecules. It is a versatile technique and is using light, electromagnetic radiation in infrared region. So in the IR spectroscopy, you get absorption band based on change in dipole moment. So if there is a bond that is not polar, there is not going to show any peaks. Also, there are two area in the IR spectroscopy. One area is called fingerprint. The other one is called like the more of a general region for the functional group. In the fingerprint area, you get information about like the whole molecule. In the higher energy level, which is based on the stretching, you get the information about the functional group. Intensity of the absorption also depends on the polarity of the bond. The areas that the peaks appear, we have some of them in this table. Approximate location for like CC double bond, it appears around 1600, and we have CC triple bond 2200, CN double bond at around 1600, and CN triple bond at 2200. CH bond, basically the hydrogen attached to the sp3 hybrid, it appears at around 3000, OH at 3300, and NH also at 3300. From this pattern, we can see that the stronger the bond is, it's going to, the peak, corresponding peak appears at the higher frequency, also, or the wave number. Also, the smaller the atom is, the band or the peak appears at the higher number. So these are some of the patterns that we could see in the IR spectrum. Regarding the functional groups for alkane, we have the CH, and the CH here is attached to the sp3 hybrid carbon, which appears slightly less than 3000, and the CC single bond, which appears around like 1200, in this area 800 to 1300. For alkene family, we have two distinct peaks. One is for the hydrogen attached to sp2 hybrid carbon. The sp2 carbon, this hydrogen appears slightly higher than 3000, and CC double bond at around 1600. For alkyne, however, we have a triple bond that appears at 2200, and the CH for alkyne, this carbon is sp hybrid, and the hydrogen attached to sp hybrid appears at 3300. The terminal alkyne, they have hydrogen, but if the alkyne is internal alkyne, there would be no hydrogen. For aromatic compound, we have a hydrogen that appears slightly higher than, just like the sp2 hybrid, it appears slightly higher than 3000, and then the carbon-carbon bonds, we get two peaks, one around 1600 and the other one around 1500. So those are the two peaks that would indicate the functional group is aromatic. If you look at the structure for this molecule given here, for this molecule, we have different bonds. We have a CO double bond that appears around 1700. We have OH that appears around 3300 with the broad peak with the round tip. So if we have the structural formula, we can predict what type of peaks we get, and if we have the IR spectrum, we can interpret that and relate or find the corresponding peaks for the given given molecule. In this slide, we have the functional groups again, and we can, based on the tables that we had and the information that we have so far, we can predict the location for the peaks. Example, we have aromatic ring here. For the carbon, we get a peak at 1600 and another one at 1500, between 14 to 1500. CO double bond at 1700, and the CH is coming sp3 hybrid, it would be slightly less than 3000. The hydrogen attached to sp2 hybrid would be slightly higher than 3000. We have here CO from aldehyde, again 1700. The hydrogen of the aldehyde appears two peaks, one at 2700, one at 2800. And aromatic is going to be the same. We get 3 peaks for aromatic, one around the 3000, slightly higher than 3000, one at 1600, and one between 14 and 1500. We have also, I just want to mention that for the CO double bond, which appears at 1700, normally CO double bond appears around 1700, but if you have resonance, it would lower that number. Electron withdrawing group would increase the frequency for CO double bond. For amides, which is shown here, since there is a resonance, formation of a resonance, the peak for CO double bond appears around 1640. But for esters, which is the other end of the spectrum, for esters, the CO double bond appears at much higher number, which is around 1740 for esters, because we have electron withdrawing groups. But here we have the resonance. Conjugation lowers the frequency. Electron withdrawing group would increase the frequency. The table that we have here, of course, it gives approximate number for many bonds that with the location based on the wave number where the peak would appear, and also intensity of the peak. If you memorize these numbers, is going to help to interpret the IR spectrum easier and much faster. So if we have the structure formula, C and triple bond, it appears at 2200. The aromatic ring, we have 1600, 1500, and 3000. This OH group now 3300. So based on the table that we had earlier on previous slide, we can predict the location of different peaks that is expected for each of these. This spectrum, we have the structure formula with corresponding IR spectrum. Just need to find and locate which peaks belong to which bond. The CC triple bond appears around 2200, so we have this as a CC triple bond. The hydrogen attached to sp hybrid carbon, it appears around 3300, so this is the hydrogen attached to triple bond. These hydrogens are on both sides of they are around the 3000. So these are the sp2 hybrid hydrogens. So we have CH and sp2 hybrid. Aromatic ring shows the CH double bond, CH sp2 hybrid peaks, and also shows these two peaks. That's for this molecule. We have alkane, so we have a lot of CH bonds, and that's why we have high intensity, because we have high population of the CH bonds, and they all appear less than 3,000. For when you have alkene, you have a CC double bond 1600, and also if you have a CH attached to sp2, is going to appear higher than the 3000 level. Okay, that's the end of the presentation. As a practice,